Okay, friction. This is not new. Friction is due to the interlocking of molecular molecular hills and valleys between a surface and an object on the surface. Although the surface appears smooth on the atomic scale, they're very, very not. So friction is a few things. First of all, it's material dependent. Different materials will have different values for what we call the coefficient of friction. To figure out what they are, these are experimentally verified. And we can decrease friction by making objects smoother or adding a lubricant of some kind, grease, is a classic one. Grease and bearings, for example. Conversely, we can increase friction by making a surface rougher, or that's really it. Friction resists sliding, and as a result, there's two interesting results here. I'm not sure if you talked about the second one in grade 11 or not, but because it's resisting sliding, it can resist motion for a sliding object, but it can also create motion for walking or rolling. The only reason you're able to walk forward is because the friction between your ground and your shoes or your feet or whatever is pushing you forward, because you're trying to push backwards with your shoes, but the friction between your shoes and the ground actually propels you forward. Something we typically don't think of. So an example here, if we have a block here and it's sliding to the right, friction is actually acting backwards. We've got a car speeding up. We've got wheels that are trying to spin on the road. As the wheel turns this way, the motion of the wheel at point of contact with the road is actually backwards. And what that means is friction at this point is actually pushing forward. And this is what actually propels a car forward, causing acceleration that way. This is an example of friction actually causing motion to happen, because it's preventing the sliding of the wheel while you're on the ground. If a car slows down, as is demonstrated here in C, there's a couple different, there's two different ways a car can slow down. Option one, using the brakes. Meaning the car is in control. Possibly no sliding, depending on the circumstance. Or two, you're depending on the surface of the road to slow you down. And if you're depending on the surface of the road, you have no control. Okay? So in one, let's say that the wheels are still spinning. So the wheel spins this way. What's actually doing the slowing down? Well, you've got brake pads. They grab onto your wheel. And this causes friction to act that way, slowing the spinning of the wheels down. This implies that you don't lock your brakes, or you have what's called an ABS system, an anti-lock braking system. Okay, that's where the friction is on a car that's just braking to a stop. If you lock it up, then you're sliding. Wheels are not spinning. Friction is between the tires and the surface. Okay, Flip page. Let's go quickly through friction. Nothing is new. The amount of friction depends on the type of surfaces that are in contact. This is represented by the coefficient of friction mu, which is a dimensionless quantity, means it has no units. If mu is large, there is lots of friction. If mu is small, there is little friction. So a small value of mu, 0.01, little friction. Steel on ice, this is why skates slide so nicely. Or 2, rubber on concrete, large coefficient of friction, 0.075. Doesn't seem like a big number, but as far as coefficient of friction goes, that's still pretty big. The force, so that's part of it. The amount of friction depends on that coefficient of friction. It also depends on the force pushing the surfaces together. The force pushing the surfaces together is Fn. In simple problems, the force pushes the object together is the weight of the object, but this is not always true. A better measurement of the force pushing the surfaces together is the normal force. And a couple examples of different situations here. So let's say I've got this block. I've got this block. That's supposed to be flat. I've got that block there. This one, these are all 2 kilogram blocks. In this first one, the block's just sitting there. Fg is 19.6 newtons. So Fn is also 19.6 newtons. The normal force is equal to the weight of the block in this case. In this next one, I still have Fg downwards. But let's say I also add an applied force. If I have an applied force downwards of, I don't know, let's have someone stand on it, 980 newtons. Downwards. Well, then the object's not falling downwards, so that means the normal force has to be accounting for all of this. That means that my Fn is going to have to be Fa plus Fg. So that's going to be 996.6 newtons. Or maybe I'm lifting up a little bit. I've got Fg is still 19.6, but I've got an applied force upwards now. Fa equals 10 newtons, which means my normal force here is only going to be 9.6 newtons. Okay? So we can increase or decrease friction by pushing down or lifting up on our object, adding weight to it, that kind of thing. We're going to skip example 2 here. We go straight to the calculation for friction. You've seen this before. The force of friction equals mu Fn. This guy here depends on material. And this guy here depends on interaction with a surface. Okay, flip the page, look at some stuff. So a student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best force diagram for the cart after the student has released it? Let's look at some stuff here. So the student has released it, so there is no Fa, which means it can't be B. It has an Fa there. There is no Fa. C tells us, well, first of all, the question tells us there's a flat, rough surface, which means there's friction. So it can't be C. And friction opposes motion, so it can't be D. It's got to be A. That's what's going on here. So go straight to example 4. Find an expression for the acceleration of the shopping cart if the coefficient of rolling friction is mu. So let's redraw. Here's the scenario. I have force of friction backwards. I've got a normal force upwards. I got force of gravity down. We know that the cart has a mass of, well, we don't know the mass. Let's call it a mass m. We know that we're going to call that direction positive. Rolling friction, I just want to be clear on what rolling friction is. This is friction from the wheel's bearings, so like the internal workings of the wheels. We know that the force of gravity is just going to be 9.8 times m. There's no other upwards or downwards forces, so we know that Fn is going to equal Fg. In this case, these guys cancel each other out. So we know that I'm looking for an expression, Fnet equals ma. Fnet is the force of friction equal to the mass times the acceleration. Oh, and the force of friction is negative because, well, that's, I said right was positive. So this is going to be negative mu Fn equals ma. So that's going to be negative mu. Fn equals Fg, so that's going to be 9.8 m equals ma. My m's are going to cancel, and so we're going to get negative mu times 9.8 is equal to our acceleration in this case, which is a fun little result. My mass is canceling. If friction is the only thing slowing you down, that is a very useful expression for the acceleration. And it's 9.8 because little g is 9.8, so this is true only near the surface of Earth. It's a fun result. Flip the page. Okay, example 5. Here we go. Draw a line straight down your page. We have two scenarios here. We've got a 10 kilogram block with a 20 Newton applied force, or we've got the 10 kilogram block with a 20 Newton applied force and a 15 Newton force downwards. Okay, so we're going to add some, and we're told that the coefficient of friction between the blocks and the surfaces is 0.12. So each one of these has, through free body diagram, force of friction backwards on that guy. This guy's going to have an Fn upwards, and he's going to have an Fg downwards. Fg is going to be 10 times 9.8, so that's going to be 98. My Fn in this case, because there's no other upwards or downwards forces, it's also going to be 98. Those are measured in newtons. Force of friction is mu Fn, so that's going to equal 0.12 times 98. So that's going to give me a force of friction of 11.76. So now I can find out what my acceleration is. Fnet equals ma, always starting there. Well, the net force in the direction of motion. Oh, and I should say, I'm going to call to the right is positive. So these guys cancel each other out because they're equal and opposite. They're also not in the direction of motion. So I'm going to have, ooh, and I forgot to label that guy there. That is an applied force. Okay. So if to the right is positive, I'm going to have Fa minus my force of friction equals ma. My applied force is 20 newtons. My force of friction is 11.76 newtons. My mass is 10 times a, which gives me an acceleration of 0.824 meters per second squared. Easy. Let's do the forces, the free body finish the free body diagram for the object on the right. We've got gravity is also acting downwards, so I've got Fg is still 98 in this case. So we've got an applied force, call that Fa1. And this will be Fa2 because we've got another applied force of 15 newtons downwards. Friction opposes motion. And because this object is sitting on a surface and that surface is flat, we're going to have an Fn upwards. Okay. In this case, Fn is going to have to equal Fg plus my Fa2. Okay. This normal force has to oppose both of these downward forces. So in this case, my normal force is going to equal 113 newtons. The sum of Fg and Fa2. That's going to change my force of friction. It's going to become 0.12 times 113, which is going to give me a force of friction of 13.56. I should have newtons on all of these forces. There. So now I can go through and I can calculate what my acceleration is going to be in this case. Always start here. F net equals ma. I want to see that. The next thing I'm going to want to see is the sum of all my forces in the direction of motion. These guys aren't included. So we're going to have Fa1 minus force of friction equals ma. Fa1 is 20 minus 13.56 equals 10a, which means my acceleration is 0.644 meters per second squared. So it's actually making it harder to accelerate forward for a sliding object. Yeah, there you go. Flip the page. Oh, actually, no. Go back. Don't flip the page. I want to make some notes here from example 4 and 5, some things that we can see here. So from example 4 and 5, some results here that are really practical and kind of important. 1. Adding mass makes forward motion or forward acceleration, I'll say, harder for a sliding object. Number 2, adding mass improves forward acceleration for a rolling object. And 3, adding mass has no bearing on stopping for a sliding object. Okay. Number 3, we saw that in example 4, that the acceleration for a I'll say this. No, for that's wrong. For a rolling object. Okay. Practical results. In the snow, you want to improve the performance of your vehicle. Adding mass improves the forward acceleration for a rolling object. Putting heavy things into your vehicle will make it easier for you to accelerate because the added mass will increase the friction between your tires and the road. Adding mass has no bearing for a stopping rolling object, which is kind of awesome. We've seen that in example 4. What we haven't seen here yet, though, is the idea of inertia. And we're going to look at inertia in a chapter here. But as far as as far as what the sandbag or the added weight in a vehicle actually does, we're gonna have to see another chapter for that. Get to another chapter for that. But these are important results to recognize here. Flip the page. Okay, so there can be friction on an object even if it is at rest, since the hills and valleys lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction, since static means moving or not changing. So now we've got different kinds of friction. We've got mu sub s, which is the coefficient of static friction. And we're going to have mu sub k, which is the coefficient of kinetic friction. And it's important to recognize that the static friction coefficient is larger than kinetic friction. It's always harder to get an object moving if it's stopped and it's sliding. Once you've got it moving, it's easier to deal with. So if you pull a desk with a force of 2 newtons and the desk does not move, what's true? Well, if it's not, it's important to recognize here static friction equals applied friction, applied force up to some maximum determined by mu s. Okay? So until these two are always going to be equal to each other until you hit the maximum static friction. If static friction were larger than applied force, that means I push on my desk and it flings the other way. Okay? It's important to recognize static friction equally opposes applied force up to whatever this maximum is. And then once you break it, the object will start to slide. So B here, it's important to recognize that is true. We'll do an example on the next page, and I'll show you kind of what I mean. So static friction is a force that varies from 0. It can be 0 when you're not pushing on an object. There is no static friction. Up to some maximum value. If we apply a force equal to the maximum static friction, then the object is going to move. We can calculate the maximum static friction using mu static max times Fn. If the object is sliding, we use kinetic friction. Force of friction equals mu k Fn. This is for a sliding object. And this is for a stationary object. Flip the page. We've got a 5 kilogram object sitting on a surface with a maximum static coefficient of friction of 0.3 and a coefficient of kinetic friction of 0.25. We want to determine the force required to move the object. And then we want to figure, see, look at this. The object is pulled with 10 newtons, find the acceleration and the force of friction. And C, the object is pulled with 20 newtons, find the force of friction and the acceleration, just like before. So here's what we've got. Draw the picture. Got my object. It weighs 5 kilograms. I've got an applied force to the right. I'm going to call that direction positive. I have Fg downwards. I have Fn upwards, perpendicular to my surface, and I've got force of friction backwards. Fn equals 49 newtons because it's equal to Fg, and Fg is 5 times 9.8 equals 49. They're equal and they're opposite because they're the only two forces acting this way. Okay, so the force required to move the object. Oh, sorry, that was really loud. Here we go. A. To move my object, my applied force must be greater than force of friction static, which means it must be greater than mu s Fn, which means Fa must be greater than 0.3 times 49, which is 14.7 newtons. Okay? As soon as my applied force is greater than 14.7, this thing's we're gonna break coefficient, we're gonna break friction, break static friction, and this object's going to start to slide. So let's look here at B. We are told that Fa equals 10 newtons. Okay, so I've got a force of friction is 10. But we're also told that the maximum static friction is 14.7. So if the object's not moving, let's put it this way, not moving because Fa is less than force of friction static. Okay, what that means is my acceleration is 0. What that also means is that Fa must equal my force of friction static. So my static force of friction has to be equal to my acceleration. It's important to think about what the results actually mean. My force of friction isn't just 14.7. It's equal and opposite to my applied force in this case. Let's look at C. We're told that Fa is 20 newtons. This is larger than 14.7. Therefore, this is what these three little dots mean. The object will slide. Therefore, we're going to use mu k. We want to find the acceleration, so we're going to use F net equals ma. So we're going to have Fa minus the force of friction kinetic equals our mass times our acceleration. Our applied force is 20 minus mu k Fn equals, what's the mass of our 5a? So it's going to be 20 minus, now mu k is 0.25, Fn is 49, equals 5a. Finish this off, we find that the acceleration of our object is 1.55 meters per second squared, and it's positive. And we said that to the right was positive, so this object is accelerating to the right. Again, with vectors, you always need a magnitude and an acceleration, and you gotta have units. So, give you some review on friction. I want you to do 2, 3, 7, and 8. There's not a lot here. 8 talks about describing the motion of the block. I want you to get very specific when you're describing the motion of the block. Use numerical values. Don't just say it's moving. Tell me how fast it's moving. Don't tell me it's accelerating. Tell me what the acceleration is. Get as specific as you possibly can. Good luck with your review on friction. As always, if there's any questions, please let me know.